ننتقل الآن إلى part 9. In this part we will apply the kinematic relationships of circular motion with constant angular acceleration to calculate angular position, angular displacement, angular velocity, angular acceleration or time. طبعا always remember that these are the kinematics equations and they can only be used if alpha is constant, and it is the case for all of the questions that we have in the book. نجي الآن إلى question 29. طبعا هذا السؤال تابع للبارت سابق هو فعليا. In the previous part we used to have the inner radius and the outer radius of the CD track. طيب نقرأ مع بعض السؤال بيحكينا بأنه in example 9.2 which is the previous example that we have solved, we established that a CD track is 5.4 kilometers long. A music CD can store up to 74 minutes of music. What are the angular velocity and the tangential acceleration of the disc as it spins inside the CD player, assuming a constant linear velocity. طبعا الآن في نقطة وحكي لنا constant linear velocity، فأنا already كاتبها بأنه this is very important. طبعا we will see why. أولا, to solve this question, since we want to find the angular acceleration, so we can use this equation alpha is equal to delta omega divided by delta t. طبعا احنا من وين جبناها القانون؟ If we go back to the kinematics equations and we take a look at let's see omega final, this one. If we send omega naught to the other side, then divide both sides by t, we get the exact same equation. What is delta omega? It's omega final minus omega initial divided by delta t. So it's basically question or equation number 3 that we have used or we will use in this part or this question. طيب, then we have to find omega final and omega initial. First of all, let's start by finding the linear velocity and we will see why in a moment. V is equal to, الآن, what is V? It's always equal to distance divided by time. So I'll write it as distance divided by time. لكن a distance here, it's basically the length of the track. So instead of writing D, I will write L. And we already found L to be around 5.4 kilometers in the previous part. So we will write down 5.4 times 10 to the power 3, which is equal to 5,400 meters divided by the time is basically 74 minutes. So we convert that to seconds by multiplying this value by 60. And the answer of this is equal to 1.216 meters per second. طيب, why did I find the velocity? Because using this velocity we will find the initial and the final omega. طبعا وين راح يكون عندي الانيشال اوميجا فعليا؟ راح تكون على inner radius. وهاي القيمة راح تختلف عن outer radius أو عفوا الفاينل اوميجا because the outer radius is different. Also, the linear speed is constant in this question. Why? Because again, we are assuming a constant linear speed. That's why V here in this part is constant. We usually say omega is constant and V changes because if we change the point at which we are finding the velocity, حسب القانون V is equal to R times omega, and omega is the same for any point on a rotating خلينا نحكي plate for example. لكن in this case طبعا again because we are assuming a constant linear velocity, we will say that omega 1 for the inner radius, we can say well, this is 1, it's equal to V divided by R1, and omega 2 is equal to V again, which is a constant value divided by R2. Now let's substitute the values here. Regarding V, we found it to be 1.216 divided by R1, which is the inner radius. I believe it was about 25 millimeters. By converting that value to meters, it's around 0.025. And the answer of this is 48.8 radians per second. What about the second one? This is let's say 1.216. And by the way, we can write it down as 1.22. You know what? I will just make it 1.22 just for the simplicity. So let's write it down 1.22. But we can keep it as easily 1.216. It's fine. Divided by 0. Now the second radius we have is 0.58 millimeters. So this is 0.058 Now, if we do the calculation for this, we get 21 radians per second. So we have basically, this is the final speed, angular speed again, sorry, this is final, this is initial. So plug in those values in the equation that we wrote at the beginning. So going back here, we will say alpha is equal to omega 2 minus omega 1 divided by delta t. So alpha is equal to 21 minus 48.8 divided by, the time in this question is basically 47 minutes. So we can say this is 47 or 74, sorry. 74, yes, 74 times 60. And the answer of this has to be negative, of course, which is negative 6.3 times 10 to the power negative 3 radians per second square. And this is the end of this question, question 29. Now let's go to question 30. This is another question we have in the book. And this is a solved problem again. I just wrote the important things in the question. In hammer throw competition, the hammer's total length is 121.5 centimeters and its total mass is 7.26 kilograms. The athlete has to accomplish the throw from within a circle of radius 2.13 meters. The best way to throw the hammer is for the athlete to spin, allowing the hammer to move in a circle around him. Before releasing it, an athlete broke the Olympic record distance of 84.8 meters. He took 7 turns before releasing the hammer, and the period to complete each turn was obtained from examining the video recording frame by frame. And those are the timings we have on the screen. I don't have to read them. A. What was the average angular acceleration during the 7 turns, assuming constant angular acceleration for the solution? طيب. أولا, what do we have in this question? What is given? We already have delta theta, which is the angular displacement. We also know what is the time needed to complete the 7 turns. So let's write down أولا what is delta t. Delta t is equal to 1.52 plus 1.08 plus 0.72 plus 0.56 plus 0.44 plus 0.40 plus 0.36, and the answer is 5.08. Yes, 5.8 seconds. This is delta t. Now let's find delta theta. What is the angular displacement? We know it's 7 revolutions because he made, or the athlete made, 7 turns. So it's basically 7 revolutions. How to convert that to radians? Because we only use, or we usually use radians and radians per seconds and radians per second square and time in seconds when we substitute in the kinematics equations. So let's convert that to radians. So this is equal to 7 times 2 pi, which is equal to 14 pi. And the 14 pi, I guess, is equivalent to 44 radians. So basically 7 revolutions is equal to 44 radians. Now to find alpha طبعا, we have to use the following equation. We say that first of all, delta theta is equal to omega naught t plus half alpha t squared. طبعا assuming that it starts from rest, so this value is 0. So basically delta theta is equal to half alpha t squared. Let's do shift solve here. We don't have to rearrange. 44 is equal to half times alpha times the time squared, which is 5.08 squared. Here we do shift solve. Write it down. Don't have to arrange. By doing shift solve, we get that alpha is equal to 3.41 rads per second square. This is for the first part. Right. Now, let's go to the second part, B. assuming that the radius of the circle on which the hammer moves is 1.67 meters, which is basically the length of the hammer plus the arms of the athlete. What is the linear speed with which the hammer is released? We want to find the linear speed. How can we do that? First of all, we have to find the final angular velocity. Then, by finding the angular or the final angular velocity, we can find the final linear speed. Then we start by finding omega final by using this equation. Omega final is equal to omega naught plus alpha times t. Now we plug in the values. Omega final in this case is equal to omega naught, which is 0, plus alpha we found it to be 3.41 multiplied by the time, which is 5.08. And the answer of this is 17.32 radians per second. Once we found omega final, now we can simply say that V final, or the linear speed once he releases the hammer, is equal to R times omega that we have just found. And the radius of rotation is given as 1.67, so we say V is equal to 1.67 times omega final, which is 17.32, and the answer of this will be 28.93, and the units, of course, it's very important to remember units meters per second. Now, let's go to part C. What is the centripetal force that the hammer thrower has to exert on the hammer right before he releases it? So we need to find F sub C. The centripetal force, it's very simple. Say that centripetal force F sub C is equal to M V squared divided by R. We already have everything we need. And don't forget that FC is equal to M times AC, which is the centripetal acceleration. The centripetal acceleration is equal to omega squared times R, or V squared divided by R. We can use both actually. Let's use this one for example. So we plug in the values that we have already found. Now the mass is given as 7.26 times, now the final speed before releasing the hammer was 28. We found it in the previous part. Don't forget the square, divided by the radius of rotation, which is 1.67. And the answer of this will be around 3,638 newtons. And let's go to the final part. After release, what is the direction in which the hammer moves? And then now we want to find the direction at which the hammer moves. Of course, we know that it moves in a tangential direction to the circle at which the point, tangential direction, let's say. So let's write it down. It will move in a tangential direction to the point of release. هيك احنا بنكون خلصنا هذا السؤال بشكل كامل. يجي الآن إلى question 31. A vinyl record plays at 33.3 RPM. Assume it takes 5 seconds for it to reach this full speed starting from rest. So basically we are given the final angular speed, and the initial angular speed is given as 0. A, what is the angular acceleration during this 5 seconds? B, how many revolutions does the record make before reaching its final angular speed? So first of all, this is given as 33.3 RPMs. We have to convert it to radians per second. How to do that? So first of all, we should know that this is the final angular speed, and this is the initial angular speed, which is equal to 0. So omega naught is equal to 0. So omega, which is basically omega final, omega is equal to 33.3 RPM. How to convert this value to radians per second? We just multiply by pi divided by 30, or 2 pi divided by 60. So 33.3 0.3 multiplied by pi divided by 30, and the answer of this is 3.48 radians per second. طيب, now since we want to find alpha, we have omega naught, omega final, and we have the time. This is the time, 5 seconds. So we can simply say that omega final is equal to omega naught plus alpha times t. Or we can say a delta omega divided by delta t will give us alpha. By substituting the values, we will say 3.48 equals 0 plus 5 times alpha. Now we do shift solve or divide both sides by 5. So we get that alpha is equal to 0.7 radians per second square. This is for part A. Now part B, طالب لنا how many revolutions does the record make before reaching its final angular speed. لما يحكي لي how many revolutions لازم أتذكر يعني طالب منا angular displacement يعني delta theta. Which equation can we use? We can use any equation we want. Let's use this one because it's the simplest equation since we have omega naught as 0. Delta theta is equal to half or omega naught times t plus half alpha t square. Again, this is equal to 0, so we cancel this term. And let's substitute the values we have. Delta theta is equal to half times alpha, which is 0.7 times time square, which is 5 square. And this is equal to عبارة عن 8.75 radians. الآن we need to find this angular displacement and revolutions. How to do that? We say that delta theta and revolutions is equal to delta theta and radians divided by 2 pi always. So just divide 8.75 divided by 2 pi to get 1.4 revolutions. And this is the end of question 31.